Hello, and welcome to a new video in the Design of Experiments lecture video series. In this video, we will discuss the preliminary steps required before conducting an experiment. The key to performing a successful experiment starts from before the time of conducting it. This is considered in what is known as the pre-experimentation planning phase. I would like to start out this video by giving a formal definition of what an experiment is. An experiment is a series of runs or trials where in each run the experimenter will vary the levels of a process's input factors and record the resulting response. It is the way that the levels of the input factors are varied that differentiates a well-designed experiment from a poorly designed one. In the previous video, we talked about how experimentation is carried out to learn something about a process or system of interest. What the experimenter is interested in knowing about the process will be set as the objective of the experiment. Outlining the experimentation objectives is the first step in the pre-experimentation planning phase. So, what are the potential things that an experimenter would be interested in learning about a process? Well, in carrying out an experiment, the experimenter can learn which input factors are significant in influencing the process response. In any process, a particular response is controlled only by a few dominant factors out of a pool of several input variables. Knowing what these factors are allows the experimenter to control the response and hence the way that the process operates. Second, the experimenter can use the findings of the experiment to estimate the effect of each input on the output of the process, meaning he or she will be able to quantify the change in the output per unit change in the input. In addition to this, the nature of the relationship between the input and output can also be identified. For instance, consider an experiment conducted where an output is studied against changes in two input factors. The following mathematical model was fit to the data collected from the experiment, where x1 and x2 represent the two input variables respectively. From this model, the experimenter learns that the output increases linearly by 5 units for each unit increase in the first input, while it decreases quadratically by 2 units for each unit increase in the second input. Remember that this is an empirical model, and like all empirical models, this model does not resemble the true relationship between y and x1 and x2. It is just an approximation of that relationship. Third, the experimenter can determine the level at which the process should operate in order to optimize the response. A mathematical model formed out of experimental data can be manipulated to find the input levels or settings that yield the best available output. The optimization of a process is a very common objective to set, and one that can be effectively accomplished by analyzing experimental results. Lastly, the experimenter can determine the level at which the process response is unaffected by uncontrollable factors. In many cases, the experimenter wishes to configure a process or a product in a way that will make it perform uniformly under various conditions. Think of manufacturing a car, for example. A car manufacturer would want his products to adhere to different climates, different road types, and different driving habits. These factors, among others, are out of the manufacturer's control and yet will have an impact on the car's performance. Therefore, it would be desirable to set the level of the input factors that are under the manufacturer's control in a way that minimizes the effect of uncontrollable factors. In the field of engineering, this is what is known as robust process or product design. That is, designing a process or a product to be robust against the variation due to uncontrollable factors. Now, these are the 4 main objectives to set when wanting to conduct an experiment. Again, having a clear objective is crucial, as the objective greatly influences the design that can be considered for an experiment. So, other than the experiment's objectives, what are the other things that must be outlined before selecting a design? Well, a natural point to consider after outlining the objectives of the experiment is to select the appropriate response that will be measured. This may seem like a simple task, but in some cases, the response variable that corresponds to the research question that the experimenter hopes to answer is not very clear. it is important to choose the response that most suitably corresponds to the problem at hand. In other scenarios, the research question may require that multiple responses be observed in order to reach an adequate conclusion. Regardless of the number of responses, the experimenter should ensure that they can be measured adequately and in a readily manner. Otherwise, the inadequacy of the measuring system could significantly degrade the results of the experiment, which will result in wasting experimental resources. Once the output variable has been identified, it's time to consider the input factors. The identification and classification of input factors is an integral step at this preliminary stage. The number and nature of input factors of interest are among the main drivers behind the experimental design selection. It is important that we take a moment to discuss the different ways by which input factors can be categorized in a design of experiments context. The first way to classify input factors is by deciding which of them are quantitative or numerical and which are qualitative or categorical. Quantitative factors are those that can occur on a naturally ordered scale. For example, time, the weight or volume of a particular raw material, or temperature are examples of quantitative factors. On the other hand, categorical factors are those that do not have a natural order to them, such as the type of raw material or machine configuration. The other important way to classify input factors is by the degree of control that the experimenter has over these factors. Factors that the experimenter can set the level for under normal operating conditions are known as the design or control factors. These are the factors that the experimenter wishes to study in order to meet the objectives of the experiment that were discussed earlier. On the other hand, there are factors that might be suspected to affect the process output but cannot be controlled within the process itself. These are the non-design or nuisance factors of an experiment. These factors can be further categorized depending on whether or not they can be controlled within the experiment. For example, consider an experimenter that wishes to study the effect of the amount of a particular raw material added on the yield of a certain process. Since the batches from which the raw material is retrieved will vary as the process runs, the batch is considered a nuisance factor. Additionally, since the experimenter will select raw materials from known batches for conducting the experiment, the batches are a controllable nuisance factor in this case. On the other hand, we can have uncontrollable nuisance factors. These are factors that can neither be controlled in the experiment nor in the live process. Once again, categorizing factors in this manner is crucial in the context of design of experiments, as will be made clear later on. Now, once factors are identified, the next step is to decide on their respective ranges and levels that are of interest to the experimenter. For example, imagine that an experimenter is interested in studying the effect of the speed of an industrial machine, which is measured in RPM, on the quality of the surface finish of a certain part that the machine produces. The machine can be set at any speed between 50 and 150 revolutions per minute. However, the experimenter knows that setting the speed to be anything less than 75 revolutions per minute will result in an unacceptably low production rate. Also, setting the speed to be anything greater than 125 RPM will degrade other product characteristics. Therefore, the experimenter decides to limit his interest in the range of speeds between 75 and 125 RPM. Next, the experimenter needs to decide on the number of levels at which the factor will be set at in the experiment. The levels are the specific values that the input factors will take in the experiment and are sometimes referred to as factor treatments. As the number of levels increases, the experimenter will gain more knowledge regarding the nature of the relationship between the process inputs and the output. Specifically, the order of the model that the experimenter will be able to fit will increase as the number of levels increases. For instance, the experimenter will need to vary each input factor at least 2 levels to estimate the linear effect of the input on the response. Likewise, the experimenter will need to vary the levels of the input factor to at least 3 distinct levels to estimate a quadratic effect. However, as the number of levels of a factor increases, the number of runs required to successfully complete the experiment will increase. This will in turn increase the experiment's cost. This is also true for the number of factors to include in the experiment. As a general rule, more runs will allow the experimenter to build more complex models with better statistical properties, but at an increased cost. Therefore, it is very important to exercise knowledge about the process to only include the factors necessary to answer the research question of interest. Similarly, one should limit the ranges and the levels to match the complexity of information that is wished to be gained. Once the objectives are outlined, response and factors are selected, and the region of interest is decided upon, the experimenter needs to choose a design to accommodate other needs. The different designs available will vary in their statistical properties. They will also vary in the sense that they will dictate the model that can be fit, as well as the number of trials that must be conducted to successfully complete the experiment. These designs will be discussed thoroughly in subsequent lecture videos, but for now, that is all for this video, and I'll catch you in the next one.